Climbs in jet aircraft are more complicated than climbs in light airplanes. The reason is that jet airplanes have large variations in airspeed, altitude, and weight. It is common for a light airplane to be at best angle of climb airspeed immediately after rotation. After clearing obstacles, best rate of climb speed is reached after accelerating a few knots and is maintained all the way to cruise altitude. On the other hand, after rotation, jets may have to accelerate over 50 knots to get to best angle of climb speed, plus approximately another 100 knots to get to best rate of climb speed. Further complicating matters for jets, there can be considerable changes in the best rate of climb airspeed during the climb to cruise altitude. The concept of break-even altitudes allows us to examine various jet climb methods. First, let's look at an all-engines climb with no configuration changes. We'll look at the flight deck view to begin. Rotation speed is 150 knots. Rotate to initial climb attitude and raise the gear after positive climb is established. After the gear is up and the gear doors are closed, the climb speed will stabilize at 161 knots and the climb will continue in this configuration. Now we will go to the altitude versus distance plot and increase the plotting speed. This next case will show an initial climb to 1,000 feet, followed by an acceleration to best angle of climb airspeed, which at this weight is 215 knots. Rotation, liftoff, positive climb, gear up, and initial climb at 161 knots. At 1,000 feet, we will accelerate, setting flaps 1 at 168 knots and climb power, flaps up at 207 knots, and continue the acceleration to 215 knots, which will be maintained in this best angle of climb profile. Going to the altitude versus distance plot and increasing the plotting speed, we can compare the two methods. Notice that as we approach 24 miles, the best rate of climb curve begins to outclimb the takeoff configuration climb. Maintaining the initial climb condition is the best method of clearing obstacles in the vicinity of the airport, but there is little difference in the two methods beyond 15 miles. Therefore, it is appropriate to accelerate to the clean configuration after close-in obstacles have been cleared. This case is similar to the last case, but instead of accelerating to the best angle of climb speed, 215 knots, we will instead continue to the clean maneuvering speed for this weight, which is 228 knots. Rotation, liftoff, positive climb, gear up, and initial climb at 161 knots. At 1,000 feet, we will accelerate, setting flaps 1 at 168 knots and climb power, flaps up at 207 knots, and continue the acceleration to 228 knots, which will be maintained in this clean maneuvering speed climb profile. Generally, clean maneuvering speed is slightly faster than best angle of climb speed and produces a climb angle that is almost as good as best angle speed while delivering a climb angle that is considerably better than best rate of climb speed. Clean maneuvering speed is normally used because it gives an adequate buffer above stall speed at maximum maneuvering bank angles, typically 30 degrees. The slightly slower best angle of climb airspeed may require a reduced bank angle limit for stall speed protection, with an almost negligible advantage in climb angle performance. For this reason, clean maneuvering speed is the preferred climb condition for clearing obstructions beyond the airport vicinity. Unlike the prior break-even altitude for distance case, this plot compares altitude versus time. It will tell us the effect on time to climb for several climb scenarios. First, we will look at an initial climb with no configuration changes. Since the procedures are all similar to the prior cases, we will use a greater plotting speed in order to see the final results more quickly. In this case, a normal cleanup and acceleration to 250 knots will be accomplished after the initial climb to 1,000 feet. The break-even altitude for time is 4,000 feet at 250 knots. This case will use a climb at 275 knots, which is the average best rate of climb speed to 10,000 feet at this weight. The break-even altitude here is 4,600 feet. Next will be a cruise climb at 300 knots. This break-even altitude is 5,600 feet. Finally, we will look at a faster cruise climb of 330 knots. Here, the break-even altitude for time is 7,200 feet. On this plot, the slope of the climb curves represent the rate of climb. Notice that the slope of the 275 knot curve, the second curve, is slightly greater than the other three, which illustrates that 275 knots has a greater rate of climb than the others. We also see that there is not a great deal of difference between the first three climbs. So there is little rate of climb difference for climb speeds between 250 knots and 300 knots. The most important thing to note from these curves is that the break-even altitudes for time are much lower than normal jet cruise altitudes. This means that the most efficient climb to cruise altitude is accomplished by retracting flaps and accelerating to the desired climb airspeed as soon as possible after all obstructions have been cleared. This is the opposite result found for break-even altitude for distance cases, where it was better to clear close-in obstacles before acceleration and configuration cleanup. Since we now know that the most efficient climb speeds should be used as soon as obstacles have been cleared, we will now look at how to manage the climb profile from obstacle clearance to cruise altitude. This picture shows rate of climb curves versus airspeed for altitudes from 10,000 feet to 40,000 feet. Looking at the maximum points on each curve, we see a large variation in best rate of climb airspeed, ranging from 271 knots at 10,000 feet to 230 knots at 35,000 feet. This would be a complicated profile to fly. Plus, autopilots are not designed to fly this scenario. Luckily, there is a simple alternative. Jet autopilots can maintain a constant indicated airspeed climb or a constant Mach number climb. Notice also that the rate of climb curves are generally flat at the top. The red line shows a constant indicated airspeed climb at 280 knots, and the green line shows a line of constant Mach number passing through the best rate of climb at 35,000 feet. Notice that where the red line and green line pass through each rate of climb curve, the value is nearly equal to the best rate of climb value at each altitude. During our climb at a constant indicated airspeed, Mach number rises during the climb. Since Mach number is the ratio of true airspeed to the speed of sound, this increase is caused by the true airspeed increase due to decreasing air density and the speed of sound decrease due to colder temperatures. Therefore, climbing at the indicated airspeed, that is the best rate of climb speed at a low altitude, until reaching the Mach number, that is the best rate of climb value at the cruise altitude, will produce climb performance that is very nearly equal to flying the more complicated best rate of climb airspeed curve. In this example, the jet's automatic flight control system would be programmed for a 280 knot and 0.7 Mach climb. When activated, the pitch autopilot would hold 280 knots until the Mach number reached 0.7, and then would automatically transfer to Mach hold until reaching cruise altitude. Let's see how a typical jet climb from 250 knots at 10,000 feet to cruise altitude looks in the simulator. In this example, we are at 10,000 feet, accelerating from 250 knots to the initial climb indicated airspeed of 280 knots. This speed will be maintained until the Mach number increases to 0.7 Mach at the Mach intercept point. The climb continues at 0.7 Mach until reaching the cruise altitude of 35,000 feet, where acceleration to the cruise Mach number of 0.8 occurs. We will start with the flight deck view. We are accelerating to the initial climb speed of 280 knots, which will be maintained by the autopilot. Notice that during this constant indicated airspeed climb, the true airspeed increases, as does the Mach number. The Mach number is seen in the upper portion of the airspeed indicator, and the true airspeed is shown on the progress page of the flight management computer display. As the Mach number approaches the Mach 0.7 intercept point, look carefully at the vertical speed indicator and watch for a jump in the vertical speed as the autopilot automatically transitions from airspeed hold to Mach hold at 0.7 Mach. There, did you see it? If not, let's look at it again. The reason that rate of climb is greater during a constant Mach climb can be seen by examining energy relationships. The kinetic energy of the airplane depends on true airspeed. As true airspeed increases in the constant indicated airspeed climb, some of the engine power that produces the rate of climb is diverted into increasing the airplane's kinetic energy. During a constant Mach climb, true airspeed no longer increases, so more engine power is available to increase the rate of climb. Looking at the altitude versus distance plot, the green line shows the constant indicated airspeed portion of the climb. The beginning of the red line is the Mach intercept point. The beginning of the blue line is the point where the rate of climb has returned to its value at the end of the constant airspeed climb. It can be seen that the beginning of the red portion of the climb is slightly steeper than the end of the green portion, demonstrating the jump in vertical speed. We now know that the previous rate of climb curves are an oversimplification. A constant Mach climb has a different set of rate of climb curves, which are higher than those for the constant indicated airspeed climb. In reality, at the Mach intercept point, there is a jump from the constant airspeed climb curves to the constant Mach number curves. Operationally, none of this really matters. What is important is that the constant indicated airspeed to Mach climb is a simple method to fly an otherwise complicated changing airspeed climb profile. Now that we have seen a combined indicated airspeed and Mach climb, let's review the entire climb profile. This procedure shows that the initial climb speed after rotation is utilized to clear obstacles in the immediate vicinity of the airport. Then an acceleration to clean maneuvering speed during flap retraction is accomplished. After all obstacles have been cleared, an acceleration to the best rate of climb airspeed is begun, followed by the transition to a Mach climb at the Mach intercept point, where the climb is continued to cruise altitude. When there are no significant obstacles present, the initial climb speed after takeoff is usually maintained through 1,000 feet to 1,500 feet. Then flaps are retracted and the climb is continued in various scenarios. Clean maneuvering speed may be used until reaching 3,000 or 4,000 feet, followed by acceleration to 250 knots in the United States, or to the best rate of climb airspeed in countries with no airspeed restriction. Some airlines skip the clean maneuvering speed segment when no obstacles are present and go directly to 250 knots or to the best rate of climb speed. Now that we have covered normal jet climbs, let's look at engine out after takeoff climbs and go-around climbs. First, we will look at an engine out climb at V2 with no configuration changes. Takeoff power will be maintained for the maximum allowable time and then set to max continuous. Next, an engine out climb at V2 will continue to 500 feet, where flaps will be retracted during a level flight acceleration. Max continuous power will be set when flaps are up. Note that the break-even altitude for distance is 18 miles. If a return for landing at the departure airport is possible, pattern altitude can be reached more quickly with a climb at V2. However, if conditions require proceeding to the departure alternate airport, an immediate configuration cleanup after close-in obstacles have been cleared appears to be the best choice. Since the engine-out climbing flight paths are shallow, airports with challenging surrounding terrain have published procedures for engine-out climbs. Here is an example. This is the engine failure on takeoff procedure for Colorado Springs, Colorado, where the field elevation is 6,172 feet. A Boeing 767 departing runway 30 or 35 left or right is directed to climb straight out to 6,570 feet, 400 feet above ground level, and then make a right turn at a 15-degree bank angle to a heading of 170. The climb would be continued to 6,900 feet, about 700 feet above field elevation, where acceleration to the clean configuration can be accomplished. Next, we will examine go-around climbs. On final approach at a gross weight of 260,000 pounds, a go-around will be initiated at 200 feet. Go-around pitch, attitude, and power are set, and flaps are immediately retracted to flaps 20. Gear up is initiated when the climb rate is positive. Immediate retraction of flaps from approach to go-around setting is allowable during acceleration with go-around power. Airspeed gain during the change to go-around pitch, attitude, and power is maintained. Remember that any airspeed increase toward the much higher best angle of climb speed will improve the climb angle. So the gain in airspeed from 138 knots to 143 knots will be kept, and the climb speed maintained at 143 knots. The plotting speed will now be increased. This next go-around involves the same initial procedure, but at 500 feet, an acceleration and flap retraction will take place during a 500 foot per minute rate of climb. The climb will then continue at clean maneuvering speed, which at this weight is 206 knots. This exercise illustrates why it is standard procedure to climb at the existing approach airspeed plus the airspeed gained during transition to the climb. Then, upon reaching the missed approach altitude, acceleration to clean maneuvering speed while retracting flaps is accomplished. Attempting to accelerate and clean up prior to reaching the missed approach altitude can lead to an unsafe flight path. Now, let's sum up our observations of jet aircraft climbs. The basic rule for jet climbs is to use existing speed to clear obstacles. Then immediately accelerate to the best rate of climb, best economy, or cruise airspeed, and clean configuration. We should also be aware that the climb profile that results in the shortest time to reach cruise altitude does not normally produce the best fuel economy nor the minimum time to reach a given distance. Compared to the best rate of climb case, the best fuel economy profile will be slightly faster, and the climb that produces the minimum time to the destination results in a considerably higher fuel burn. The most economical flight can best be determined by allowing a computer to fly various scenarios for a particular flight, including the effects of altitude, climb and descent profiles, wind, and routing.